So thank you so much for coming to my talk, and I want to thank the organizers for inviting me to this nice conference. So, yeah, as announced, my talk will be about BV formalism. But I want to give it a bit of a different spin. And I think, well, there were many talks here which introduced a setting. This is more of a, a shopping list for a setting. So I'm going to actually tell you what construction I'm thinking about, so what kind of examples I'm able to construct. But the setting itself is actually under development. So it's more like a homework than a talk. So if people have some idea of how to put all of this in a very nice category, then please let me know. Because this is one of the things I'm very curious about. So what is this about? Let me give you some background about my motivation to do all this. So I come from functional analysis, mathematical physics, so formalism called algebraic quantum field theory. I'm not going to talk about algebraic quantum field theory, but for those of you who don't know what it is at all, here is just the main idea. So in AQFT, this goes back to the 60s. Hagen-Kastler had this idea to axiomatize QFT in terms of C-star algebras. So they were all working on Minkowski spacetime because that was the thing at the time. So the idea was that you take bounded regions of Minkowski spacetime, and then you assign to them algebras of observables that are C-star algebras, or alternatively, there is a version of this framework with von Neumann algebras. Okay, and then what you want from that, you want some sort of, axioms that this assignment needs to fulfill. And one of them, which is actually very important, and I'm going to state it first. Well, okay, so maybe the first one, just to make things kind of better defined here. So if I have inclusion of subsets, that implies inclusions of algebras. So that's kind of a basic requirement here. And the other one has something to do with causality, causal structure of Minkowski spacetime. So if you are not working every day on Lorentzian manifold, then that might be a bit exotic. But on Lorentzian manifolds, we have causal structures, so we can distinguish directions of different types. So here is a sort of, very simple example of a Lorentzian manifold. So it's two-dimensional Minkowski. Oops, I guess I did it the wrong way around. So the space goes this way, time goes this way, and the metric here is diagonal with 1 and -1 on the diagonal. And then in this metric, obviously it's not positive definite, so there will be null directions. And I think I have do I have the correct color? I think so. So there will be the light cone. So this is the null directions. And there will be directions that are, the vector is of positive norm, quotation marks, with respect to this. So these are time-like, okay? And there are directions which are not. So these would have negative norm, so these are space-like. Okay, and then quick crash course in physics. So in special relativity, you have this postulate, of Einstein, that things that are space-like separated don't know anything about each other because nothing travels faster than light. Light travels on the light cone. Observers travel on time-like curves. So things that are space-like from each other have to be somehow independent, okay? And this is the sort of motivation for the locality, well, causality axiom. So if you have O1 space-like from O2, this is a very suggestive notation for space-like. So these are space-like separated. Okay, and then I want these algebras to commute, okay? And this commutator is in terms of a larger algebra such that O1, O2 are both contained in O3. Okay, so that's the basics. So somehow, always when I'm trying to, construct algebraic structures, I'm going to drop this C star von Neumann story, but I'm going to keep this causality relation. So somehow this is something that I need to have in my framework, whatever abstract formalism I choose. Okay, so now there is this nice framework, algebraic quantum field theory, but constructing models is hard. So in the meantime, people started doing something else. And well, in the 90s, there was this idea to maybe slightly weaken those axioms, and instead of working with C-star algebras and von Neumann algebras, just to work with topological star algebras. Okay, so then you can construct more models, and in particular, you can construct models that are somewhat relevant to particle physics. And well, this came relatively recently, let's say. So therefore, the progress is, well, still in progress. Now, I think for maybe this audience, the important point was the arrival of the BV formalism in the game. So I was partially guilty for that. So there is a way to construct models. There used to, well, for a long time, there was a way to construct models for scalar fields within appropriate weekend framework. But the actual construction for gauge theories came much later. So 2007 was the first work by Holland. Okay, and then 2013 was my work with Redenhagen. So this is gauge theories and formalism. Okay, so now I'm going to tell you about the construction. So the idea is that I'm going to construct a differential graded algebra. So there is some graded algebra. Okay, there is going to be some differential. So this is a quantum BV differential. Okay, and well, this is essentially everything that one needs to encode the information about observables, and well, maybe Owen is going to talk about this a bit in the factorization algebras setting. And I want to be able to assign this data to, well, more generally, not just regions of space-time, but to a class of space-times. So this will be assigned to M, where M is a Lorentzian manifold. Okay, assumed globally hyperbolic. So M is essentially some Riemannian manifold cross R. Okay, so now how am I going to construct it? I'm actually going to construct it through deformation of some classical data. So deformation of classical theory. Okay, and the classical theory here will be, well, some algebra, so the same graded algebra. Maybe let me add here formal power series in H bar. Okay, so everything is going to be in terms of formal power series. So in the classical theory, I do not have that. So some graded algebra with another differential. And let me here maybe explicitly write the product in this algebra. So the deformation, the way I think about it, and maybe the IQFT community thinks about it, the deformation is the deformation of the product. So the quantization here, the quantization is going to take this data to a different differential graded algebra where we deform the product. Now, there's another way of thinking about it, and this is closer. So this, let's say, is perturbative AQFT. Okay, and there is a way to think about it which is closer to what Costello and William have done, which is deforming the differential. So this is maybe a different viewpoint. So I'm leaving the product the same and deforming the differential. Okay, so that is more like this kind of story. Aha, okay, I should add H bars to it as well. Sorry about that. And yes?
Just to get an idea, this A, is it some kind of local functional?
No, it's not. No. Mm-hmm. Is it what? I'm going to tell you in a second. I'm going to define it. I'm just giving sort of overview. Yeah, that's the talk. That's the talk. This is the introduction. Yeah, and there is a relation between these two. Okay, so now let me answer Thomas's question. So everybody is dying to know. Okay. Well, I can maybe leave it here for now. So I'm going to start with the classical story, and the classical story is already going to take a bit. So a quantization will be like this tiny bit of the talk. So classical, I'm going to focus on the example of the scalar field because this is, well, relatively simple. So scalar field example. Okay, so first of all, well, we start with a space-time. Okay. Now, the space of fields or field configurations, this would be smooth functions on M valued in R. So these are fields. And now, okay, part of Thomas's question. So what sort of observables we want to have in our algebra? So classically, in the first instance, well, an observable corresponds to a measurement, so assigning a number to a field. So in the first instance, observables are functionals. Okay, and we start, okay, so this we equipped with the Fréchet topology. Fréchet topology. On such spaces, we have smooth calculus. So we take the space of smooth functionals on this space, valued in complex numbers. And here we, well, by smoothness, we mean smoothness in terms of Bastiani. Smooth, what it means? Well, essentially that Fréchet derivatives exist everywhere in all directions. And then, if you have a derivative point phi in the direction of psi, so as a map, okay, maybe I should start at the other end. So if I have point phi, direction of psi, so this lives in E cross E. I assign to it the first derivative of a functional at a point in direction psi. This is supposed to be continuous in the product topology. So that's the differentiability, and then I iterate it and I get smoothness. So that covers that. So you see this is a big space. In this space in particular we have local functionals that most people here would relate to. So f log is inside C infinity of that. So these are local functionals. Okay, and they come from integrating a function on the jet space. So they are of the form f of phi is the integral of some function of the finite jet of phi at point x with some measure. Okay, that goes over M. So these are local. They don't form an algebra. So if I want to have an algebra, I need something at least slightly bigger. So there is an obvious product. So product. So f dot g, this goes for any smooth functionals. Obviously, they are functionals into complex numbers. Complex numbers can be multiplied. So this is defined just as you think it should be. So that's the pointwise product. That's essentially the product in the classical theory. And we can complete sort of algebraically the space of local functionals with respect to this product. So space of multi-local functionals is the algebraic completion of f log. Okay, now you might think, okay, so that's probably enough, right? Why do we need anything else? There are actually other important structures that I'm going to need, and well, on that board there is, so the dot product there is the same dot product here, so that's the classical product. For the purpose of quantization, I will need another product, this T there, and the space of multi-local functionals, the way defined here, is closed under that product. So I actually need to extend that space to something larger within the space of smooth functionals so that it's closed under that product. So that is actually a motivation why we need to go a bit beyond the local setting that classical theory usually works in. So for classical theory, I would be almost okay with staying with this, but for quantization, I actually need a larger space. Okay, so that's for later. Now you're wondering about the PV setting, where it comes to. So I'm going to, as I said, look for the scalar field example. So here we don't have gauge symmetry, so that's going to be a sort of, half of the usual PV story, where we just have a Koszul complex. So let's try to do that in this example. Okay, so I have smooth functionals. In order to introduce dynamics, I'm going to do this using the Lagrangian formalism. So the equations of motion are going to be given in terms of some one form on the space of fields. So dynamics, okay, so this is given in terms of a one form. So let's call it dl. So this is a one form on the space of fields. Now I should tell you what I mean by that. So E is a vector space, Frechet vector space. So that's actually relatively well behaving. So here I'm going to use the definition of tangent and cotangent bundle from the convenience setting. I'm going to mix a bit settings. This is, you see, this is the shopping list. Some things in here are better done using locally convex setting for infinite dimensional differential geometry. Some things are better done in convenient setting. That's somehow life. They both coincide on Fréchet spaces. So this is Fréchet. So that's why I can get away with a bit of switches between settings. But again, maybe there is some better way of saying it. Please let me know. I'm just giving you a sort of practitioner's view. Okay, so what do I mean by that? Well, first, I want to tell you what I mean by a cotangent bundle of E. So again, well, here E would be, well, it is in itself a vector space, but M is non-compact, and it's actually better to model this on the space of smooth compactly supported functions. So this is actually going to be E cross E compactly supported. So this is that. Okay, and then the cotangent bundle, this is E cross E, not star, sorry. Dual, this is a strong topological dual. So
you mean fiber compact, not the base?
the fiber, yeah, that's correct, yeah. So like, so vector fields, yeah, are kind of, you can think of them as compactly supported perturbations somehow, if you want like intuition about it. So this one form, right, in this setting is a smooth map from E to EC prime. But in practice, actually, this is a bit better. So, well, let me make a bit more room for myself here. So in practice, so this is the space of distributions. So the dual of the space of compactly supported functions is the space of distributions. Inside, there are distributions that actually happen to be smooth sections. That happens a lot. And there is a canonical embedding of that space. Now I just need to I need to specify what sections they are. I can be a bit more precise here, I guess. So first, I'm going to take the dual sections of the dual bundle and tensor it with densities. So if I have an element of this space, so an element of the dual section of a dual bundle and the density, then I can integrate it with something which is a compactly supported section, right? So I can do it here on the side. So if I have U in this space and I have F in EC, there is an obvious map U integrated with F, right? So this is an element, this assignment, an element in EC prime. And for the convenience of notation, so I don't have to write too many things, this whole thing will be E shrink. Yes. Prime is the full continuous dual, and star is here, E star is smooth sections of the dual bundle. So this is way smaller. This is just smooth sections, and this guy is distributions. Okay, so that's what it is, and as I said, in practice, this DL is actually a map from E into this smaller space. Where is the question? There is no straight E. I'm sorry. Yes, yes, I'm sorry. I was doing it in general, yes. So I guess in general. Yeah. Sorry about that. Yes, thank you. So here straight E is just R, so this is a bit of an overkill. But yeah, just, you know, like obviously we are looking at smooth functions in value in R. This story with duals is maybe a bit of an overkill. But just so you know how to generalize it. Thank you for the question. All right, so now that I defined what that actually is, this one form is giving me the equations of motion. Okay, so this is essentially this statement. So phi is a solution. Phi is a solution if it satisfies this condition. So phi is in ES, which is the space of solution, which is inside E. Okay, so that's the equation of motion. And now I'm interested in, sorry? Do you have a question? No, this, okay. Okay, I get it. If phi satisfies dl of phi equals 0, then phi is a solution, and we use notation ES for the space of solutions. Okay, now it's a full sentence. All right, so let's, yeah? The what?
Is DL D of something or not necessary?
No, it's not. There is a story there, but no, it's not. It would be if M was compact, but it's not. So, but it's close to being D of something. But we can talk about it later. That's why I'm using this slightly suggestive notation. All right, so now I want to characterize the space of functionals on that space, which are on the space of solutions, which are my favorite type. Favorite type for now is multilocal. So I'm interested in whoops. DL? Is it closed? What do you mean closed? Is it closed? Yeah, it should better be, yes. Yeah, I mean, yes, it is. The question is not as trivial as it sounds, but yes. So, interested in the space of multilocal functionals on the space of solutions. And this I want to see as a quotient of all multilocal functionals over the multilocal functionals that vanish on the space of solutions. So these vanish on ES. Okay, great. So now I want to, this is the spoiler, I want to resolve this quotient. I want to use Koszul complex to find, homological interpretation for this quotient. And it's essentially going to be my classical BV complex, so the classical story there. Okay, so here there are some subtleties. So first of all, the usual way of doing things is you say, well, I take vector fields and then I have the insertion of that one form as my differential. I need to take a space of multi-vector fields that are also, well, these vector fields for now are also of this multi-local type. So take multi-local vector fields V and L. Now define differential. So S is defined as insertion of this one form dl. So we have here multi-vector fields S to multi-local functionals. And here, now we take multi-vector fields. Multi-vector fields. So then we have higher exterior powers of that, and ba-ba-bum. And the grading here is 0, -1, -2, and so on. And now, fact, which I'm not going to prove, but it is proven elsewhere, is that here, well, the image of S, so when you insert this one form to a vector field, obviously you get something that vanishes on shell. Sorry, that vanishes on the space of solutions. By definition, it's not super obvious that this is all of F0, but it is. So fact, no proof. But again, whatever generalization I'm thinking about for this, you know, if somebody gives me a nicer way of viewing this setting in terms of some, you know, more fancy graded geometry, I want this fact to be also true in that setting. So the image of S in degree 0 is exactly FML0. Okay, so then obviously H0 of S is this space of multi-local functionals on shell. Okay, that's what I wanted. Now for the scalar field, this actually happens to be a resolution. I'm not going to use that fact anywhere, so just fun fact. For gauge theories, this is not a resolution. Some further stuff has to be done, but not today. We're doing the scalar field. Okay, so that's where the graded story comes in, right? So here you can see what my A is going to be. So A is this exterior algebra over, ML is missing, over multi-local vector fields with this differential S. Done. Now, where is the deformation coming in? So there are some very nice results about, well, actually the properties of this equation. Well, I wrote there dl of phi equals 0 in a certain class of theories. So, well, first of all, we want that form actually to be local. Well, that is definitely compatible with what one does in physics. Moreover, this condition dl of phi equals 0 would be expressed in terms of some differential equations. So that's essentially the locality here. So here assume dl to be local, so that dl phi is a differential equation for phi. So in particular, let's look at the free scalar field. So example, free scalar field. Okay, this dl of phi, it's going to be the D'Alembert plus m squared. This, let's call this operator p, applied to phi. And if I want to be consistent with these densities as well, I might want to multiply this whole thing by some volume form, so I really land in the space E-shrig. But the key thing is to study properties of that operator P. As you can see here in this example, this is a very nice operator. So these equations are what one calls normally hyperbolic. So normally hyperbolic equations. And there is a lot known about the space of solutions for such equations. I think I'm close to the 50 minutes mark. Is that correct? Can I take 5 more minutes?
Well, you still have 15 minutes.
Oh, really? Oh. Oh, all right. Well, yeah, I wasn't paying attention. Well, that's great. That's great. I thought, I have to erase the board then. Awesome. So we have those equations, and there is a lot known about the green functions, propagators, and so on. I don't give you the full story because it's more than 15 minutes, but I want to give you part of the story. So you can, so there exist distinguished green functions for P. Okay. So in particular, there are so-called retarded and advanced green functions. So retarded / advanced green functions. Okay, so I know that delta is used for different things in VV formalism, but I have to do this. Okay, this is not the Laplacian. This is not the Laplacian. This retarded advanced green functions. Delta R. It's too many things are called delta, I think. And apart from being green functions for P, they have the properties okay, so if you apply this green function to a compactly supported F, okay, then the support of that is going to be contained in the future for retarded and past for advanced of support of F. This has consequences, okay? So here, well, there are good things and bad things about it. Here is a good thing about it. I mean, these guys are uniquely defined by this property, okay? I should say there exist unique retarded advanced functions. So this is the R. Talk still visible when you come to the conclusion. Okay, so what am I going to use it for? There is another green function that, well, I'm interested in, which is called the Feynman propagator. And this is defined as I have sum over these guys plus an extra. Okay? So this is some symmetric solution for P by solution. So P, when applied to H, gives you 0, so kills off H. Okay, this is somehow determined. Well, I mean, there is no unique choice for that. There's a whole class of these things, not unique. Yeah, you can you can apply P from the right. so yeah, in both ways is 0. Okay, and this guy is going to be important. So this guy I want to use to define that product T that I have above. So I want to define, so for Fg, okay, multilocal, I want to define the time-ordered product, okay? And here is a formula. I think it's best if I write it this way. And we just need to parse it a bit. So it's going to be an exponential operator. So I'm going to take derivatives. I can do this because I have small fractionals of f and g. Okay, f and g. Then this pairing is just a pairing of, well, given by integration. So this is some distributional kernel. These derivatives would also give you some distributional kernels. And then I multiply them, integrate them. Here I need some h bar, because this is a formal definition. And here I need to multiply everything together so that I'm at the same point phi. So that's the definition. And this guy here is called time-ordered product. Okay. So that definition, the way I wrote it, doesn't actually work for all elements of F multilocal, so caveat. Okay, so F, G, maybe, okay, so there is a bit of subtlety. So this is the first definition you would write, which should work if we didn't have any singularities of this propagator and these derivatives. So this the first attempt, which actually has to be made precise. So caveat might need some, well, there's going to be a problem with taking powers of these distributions. Multiplying distributions at a point is always a bad idea. So if you want to do it, you have to be super careful and, you know, have your book of Hermander with you when you go into the battle. So you might need to do some distributional extensions. So you might need to work on these products a bit. Some extensions for the powers of delta F, okay? But now I'm kind of focusing on algebraic structure, so that procedure here of distributional extensions, so that this is nice and kosher, this is going to correspond to renormalization. And everybody knows that renormalization is a mess. So, renormalization. It's clearly a physics talk because I said renormalization. Okay, but there are then nice things about this product, modulo, well, all the caveats, but first observation, I mean, even without that sort of distributional story of, you know, whether I need to extend or not and point to that, you notice that I have two local functionals, let's say. I multiply them with this thing. Delta F is non-local. So there is no way this can remain in the space of local or multi-local functionals. That's to be forgotten. So I need a larger space which is closed under this product. So need larger space of functionals. Okay, and this is called F microcausal. Not going to define it because that's a very sort of messy thing. You need to control some regularity properties of those distributions. So microcausal functionals. Okay, so some regularity conditions for derivatives. All right, but there exists a space like that, and F microcausal formal power series is now closed under this product. Done. Closed under T. Okay. The last. That's correct, yes. D squared over d phi squared. This gives me the equivalence of products. Okay, homework. You can check that real quick. Okay, and I can use this map to deform the differential. So deform S. Okay, so I define S hat is T minus 1 composed with S composed with T. We are in the free scalar field situation. So that's the definition. You know, nothing wrong with the definition. But then there is a calculation. So here, calculation. All right. And this in the zeroth order in H bar, well, you can guess what that is. That is S. And then in the higher order of H bar, there is something which corresponds to the renormalized PV Laplace. So this is renormalized. Distributional story, kind of packaged in a more category theoretic setting. So all this stuff that I pushed under the carpet, I would like to be able to push it under the carpet. without feeling guilty about it. So my question to the audience is somehow, is there a setting which is beyond locality, right? I need some non-local objects here, which would allow to, do all these geometrical moves within that setting, and also, that controls somehow regularity of distributions. Okay, so that's the homework, and with that, let me thank you for your attention.